So last week we discussed the physics about basically how photons can dislodge an electron and basically start the current, and we basically said they use this phenomena in order to make a p-n junction. That's basically our solar cell. You put the photon flux on it and current will start flowing. And we said as users of this photocell, we basically all we care about is the curve that represent the output power out of this photocell. So some current will go through the junction, but then the useful will go through the load. So you can see how the G load, the useful energy or the useful current, is that whatever is generated from the sun minus whatever is leaking through the junction, right? And so this equation then translate into this curve. And so this is the current, this is the voltage. We care about output power. The power is this guy multiplied by this guy. And so you multiply the current times the voltage and you'll get that curve. And so this point is what we care about. This is the point of maximum power. And so the current and the voltage at this point is our design current and voltage. We are not going to run at the maximum voltage because that is useless. Maximum voltage, you can get it at zero current. So power output is zero. Right? So we will run here. Right? And we finished last week by saying that you need to note that as you send more and more photons, you will get more and more electrons. So chances are the output power from the photocell or from the whole PV panel is going to be proportional to the incident radiation. So if you get a stickers on the PV panel saying 300 watt, that 300 watt will go up and down depending on, are you sending one sun on me or less? So instead of sending 1000 watt per meter square, which was we called one sun, if we get 800, don't expect yourself to get the sticker rated power. You're not going to get 300 watt. You'll get less. Okay? And by how much less, we will see today, but it's going to be the ratio. That ratio between the output, the incident radiation to the rated radiation. Okay? So, just like solar heater, PV panel also come with something like this. And you will see maximum power 200 watts. Okay, and when you will get this, look at that. You will get at 1000 watt per meter square. And the temperature is 25 degrees C. And AM is 1.5. What is AM 1.5? That is called the air mass ratio. And what is the air mass ratio? So this is you. My kids once saw me my lecture note one time like this. They are in the 5th grade and they said, "Daddy, you draw like sticks, like stick figure. What is that?" And like, I said them, "It's fine, don't worry." They were like concerned like how I don't know how to draw. So if the sun directly above you, alpha equal, how is the sun can be directly above me? Alpha should be, help. If the sun is directly above me, above my head, my shadow is under me. Alpha is 90, perfect. If alpha is 90, it will be directly above our head, and the sun will move into the atmosphere the shortest distance ever. It will go through this 10 kilometer atmosphere, that's the shortest distance. But if alpha is less than 90, the sun will go through longer and longer atmosphere. Okay? So at sunrise, at sunset, that will be the longest distance ever. Right? So what's the problem? At the point it will reach us at the end, right? No, there is a problem. What is the problem? Huh? Forget about clouds. Clear atmosphere. No cloud whatsoever. What's the problem with like going a lot through the atmosphere? The air molecules. All those air molecules will start scattering the radiation. Okay? And that's why in sunrise and sunset the sun look orange or reddish. Why? Because that is the one that remain. All the other wavelengths get scattered. So the blue is the easiest one to get scattered, and that's why every time we look to the sky we see that blue dome. Why the blue dome? Because that is the first light to get scattered. So all the short wavelengths like the blue, they all get scattered, right? But still we get a lot, and that's why the sun look kind of whitish most of the day. But at sunrise and sunset, because this path is so long, everything gets scattered except for only the red that show up at the end. Okay, it's like the atmosphere is doing X-ray, so you only see the ball. That's what's only left in the picture. All the other things disappear, right? So my wife was super impressed by me when we were still like engaged, and I explained to her why the sunset is orange. She's like, wow, that's why. So that will make you score really high with your significant other if you explain to them why sunrise is red. Okay, so now the ratio between that shortest path to whatever you got is the air mass ratio. So when the air mass is 1.5, that means that the sun is doing 1.5 the shortest distance that it should have been able to do. Okay, and if you are wondering, okay, we got why the color is blue and red and stuff, but how is that affecting the solar cell? Wouldn't the solar cell just care about the watt per meter square? Why does it care? Like at the end of the month, don't you just care about how many dollars do I get in my pocket? Why do you have to care whether this was steps or this was salary? Why the division? I just got my whatever 5K per month. No, the solar cell care where the money is coming from, where the photons are coming from, because the direct radiation has an angle. The other radiation, the thing that gets scattered from the sky, come from everywhere. It doesn't have an angle. So for some of them, we'll see some of them called concentrating solar cells. So rather than having a big blue thing, they have a tiny blue thing, but it's very expensive tiny blue thing because it have multiple junction, and they have a lens on top of it that focus all that radiation in that tiny expensive cell. So they care about whether I can direct that toward me or this thing coming with an angle. Also the fact that it's coming with big angle mean if the radiation is coming not normal but coming with big angle, what will happen? It will reflect a lot. So you are telling me I'm giving you 1000 watt. Why you are not giving me my rate power, but you are giving me 1000 watt and 50% is coming with a big angle? They will not even go through the glass. They will reflect from the glass. So bottom line is you only get your rated power if you deliver exactly those specs. 1 watt and air mass 1.5. Okay, so the maximum power is 200 watt and the voltage at maximum power 26.6. So if you connect the terminal from this, you get 26.6, and that point of VNB and IMB, the current at maximum power and the voltage at maximum power is exactly this point. So he's saying this is 26 and this is whatever the current he said. Okay. The open current voltage is a little bit bigger. So rather than 26, 32. That is what? That is this point. Okay. And look at those numbers. Those numbers is 0.5 volt and stuff. And here he's saying 26. Why? Because he doesn't put one cell. This panel consists of a lot of cell in series and a lot of them in parallel too. Right? And there's a bunch of problems about this. Like when we are stacking those photocells together, how many by how many? Is it 5 times 4 or 8 times 3? How are you going to stagger them? and we will stagger them so that we can get that voltage. So if the voltage of each cell is 0.5 and you want to get 26 voltage from this panel, you better need what? How many in series then? 26 times 2. If you want total 26 volt and each one of them is giving you 0.5, you just 0.5, 0.5, 0.5, 0.5, right? So you need 26 times 2 to get that 26 voltage, right? And now if you need how many in parallel, it depends on the power that you want to generate. So you calculate the power of each one, and you say, well, then I need 2 rows, not just 1 row, or 3 rows, or 4 rows. Right? This is the dimension, and that's what it will take on the on top of your roof, right? Yeah, and so here, so he's basically telling us that if you increase the incident radiation, expect more power output. Can I make this bigger? So here's one sun. Here is 800 watt per meter square. Here is 6. Okay, so it's obvious that this equation, and actually this equation is, we can assume it's linear. The power output is linearly proportional to the incident radiation compared to us 1000 watt. You give me the 1000 watt, I'll give you rated power. You give me 800, then I'm gonna give you 800 divided by 1000 times the sticker price, or the sticker rated power. Okay. So temperature sensitivity for 200 watt module. So look at this. The power is minus watt per degree C. So if you make it hotter, he will not deliver that power. This is the penalty for the power output. Okay. So over here, I am saying that, so in order for one to calculate the output of this thing, you need correction for the temperature, and for that we will need a lot of we need information from the supplier. What is that relation between the power output and the cell temperature? Okay. Fortunately, we are not going to do this. We are going to make it much simpler when we are designing those systems. Okay. But you need to know that it's function of temperature. And that's why in photocell or like PV panels, when they install them in the house, they give you a control panel that tell you what is the temperature, so that you would see how hot they are, and you can monitor the temperature and the power output as function of that temperature. This slide is explaining that we wish the curve was rectangular, but it's not. It's basically, it's a curve, and that reduces the Pmax from what we could have achieved has this curve been a rectangle. And that ratio between the open circuit voltage and the short circuit current multiplied by each other, which is the maximum ever, and between the actual maximum, that ratio is called the FF, the fill factor basically. Okay, so he's saying one calculate this maximum power by multiplying V open circuit times the I short current multiplied by this FF. Okay, so he will either give us directly this Pmax, or he will give you those two guys and the fill factor. It's two ways to basically tell you how much power you should expect from this thing. And here, this is the part when I say 1000 watt per meter square at air mass 1.5. That's what will give you the sticker rated power basically, right? And one should also expect that as this thing gets older, the efficiency drop. So every year the efficiency, you should expect it to drop from you, right? So here's the first kind of problem. Here is one photocell, and he's saying basically how we can arrange them. Okay, in module, and then at the end of the day in the PV panel, how many we should have. So adding them in series, you increase the voltage. Adding them in power, in parallel, you increase the current. Right? Just like any battery. Think about this photocell as really a battery that's just powered by the sun rather than by chemical reaction inside. Okay? So here is the example. He's using the AH class. He's giving different classes that they can make in that factory. Well, here's the AH class. What is it? Power maximum voltage at power maximum 0.49 volt. The current 5.13 ampere. Again, those 2 points at the maximum power point, which we care about. Right? We don't care about the open circuit voltage or the short current. The short circuit current. We don't care about this. We care about those two guys. And he wants to put them together to make 12 volt and 120 watt panel. The panel should have a total voltage of 12 volt and maximum power of 120. And when you go to Lowe's or Home Depot and try to buy one, you will see that they look like this, like the blue, and then there is copper wires or some wires moving on the top. So, and it's really thin, huh? So this is the top, the blue is like the positive, for example, and the other side is the negative. And so to connect them in series, those current or those wires need to collect the electrons and then send them to the bottom of the next one. So the wire go from the top to the bottom, from the top to the bottom, from the top to the bottom, right? Because each one again of those slices is basically positive and negative. Alright? So what is his problem then? He said recommend an arrangement that will meet the specs. Okay, so I look here, 0.49, I want 12 volt. How many in series? How many should I put in series if I want 12 volt and each one of them is 0.49? 12 over divided by 0.49, right? 12 over 0.49, it will become 24. 12 over 0.49, it become 24.3. So obviously I need maybe 25, because 24 will make me short. I'm not going to get 12 volts. I'm going to give him 11 something. So I go higher. Okay, so I want 25 in series to get the 12 volt. Now the maximum power we want is 120 watt. We want to say this, give me 120 watt. So I will divide the maximum power, which is this guy times this guy, it's 2.53. That's the maximum power you get. 2.53. 120 over 2.53, it's 47.4 cell. So you need total 47 cell, and you need 24 in series to get the right voltage. So what is the deal then? What we're gonna do? Maybe 25 times 2, right? 25 times 2, that will give us enough. Alright, we'll go a little bit above, but that's how we do it. Questions? You got this? Voltage, control how many in series. The total power, control how many total. And you divide the total over number of how many you want in series, and it will tell you the range. Okay? So that panel would be 25 multiplied by 2. So 25 in series, 2 passes. Alright. So, good. So now, here is a bunch of system that is already operational in different cities. Okay? And this is during the lifetime of the project. And this is the kilowatt hour generated. Okay? What is this cycling? What do you think going on? Summer, winter, summer, winter, summer, winter, summer, winter. Very good. Okay. So the installed is 73 kilowatt on the roof, But right now it's generating at 10 a.m. July 11, it was generating 36 kilowatt. How come? Because they are not delivering the 1000 watt per meter square with air mass 1.5. And why they are not generating the 1000 watt per meter square? Well, first, like what Jairo said, it's flat, so I mean maybe they should have been normal, especially that it's 10 a.m. so the sun is not really high. Also because they are in New Jersey, so maybe the sun is actually it's never really that high, so the air mass is a little bit bigger, a lot of scattering. So a lot of reason will not make you generate the rated power. Okay, so this is annoying in designing the system. So if I am in, like, they give me Walmart over here in South Tulsa, and they said, okay, we want to be the greenest Walmart in the whole country. Give us order for us as many PV panel as you want. We just want to run exactly all year long on solar energy. So I know that and they said our maximum power is this much. Here is our HVAC system, here is our fridges, freezers, everything, lights, and we require this much kilowatt. We never go above this kilowatt. And let's call it 40 kilowatt. They require 40 kilowatt maximum in that place. Like it's a small neighborhood Walmart, not the big one. And they require 40 kilowatt. So how much should I buy? Should I buy exactly 40 kilowatt or 80 kilowatt or 120 kilowatt? And I bet if I'm in Tulsa, Oklahoma, it will be different. If I am in Arizona, different from if I'm in Alaska. I went to Hawaii one summer for a conference, and I went to Walmart. The Walmart in Hawaii have an ocean view. I was like, I wanna quit my job and work for that Walmart. So basically, you come out and you have the beach. You can, and it's higher, even not just like on the floor, like the mountain top thing, and you see the ocean and the beach. It was awesome. So anyway, so a Walmart in Hawaii will have different roof characteristic than the Walmart in Alaska, right? So how do we do this connection between what we install and what we will get? Okay, so let's see. It's something called the regional factor, RF. And in short, the regional factor is, so over here, this is the kilowatt hour delivered during this is during the year, and he basically for every month you can see how much kilowatt hour they delivered. Okay, and we can see the regular variation between the summer and the winter during the year. But if we divide the kilowatt hour during that month time the kilowatt on top of the roof, I put 40 kilowatt worth of PV panels. Okay, and I get, in this place they put 236. Okay, so they have 236 kilowatt of PV panel. Okay, 236 worth of PV panel, and they get this much kilowatt hour during the month. So if you divide this over this and you get 75, first, what's the unit? What's the unit of this number? Hours. This is hour. And what does it really represent? What's the physical meaning of those hours? What does the 75 hour represent during the month of whatever, July? What does it mean, 75 hour? Dividing the kilowatt hour we got during this month by the kilowatt on top of the roof, the installed power. What does the 75 represent for a free quiz? Like you go to your boss and say, you know what, we get 75 hour during July. 75 hour of what? No. You are almost there. You're gonna get figures of your reward. Rather than saying maximum peak hour, what do you want to say? You get 75 hour of no one got the free quiz yet. You get 75 hour of huh? No. You get 75 hour of 75 hour of no. Yeah, say it. If you just say what's this ideal condition, you get a free quiz. No. You get 75 hours of one sun. The sun, so you are all focusing on the output. It's the input. It's as if you get 75 hours of one sun. The sun is radiating at 1000 watt per meter square for 75 hours during this month. And for the rest of the sun, for the rest of the months, the sun is zero. The sun, so the characteristic, not just in New Jersey during that July, but it's also the tilt on that of that collector and the sun make it such that you get 75 hours of one sun during the months, and for the rest of the months the sun is zero. Okay, so this hour per month is very useful because that's all we need to figure out if this is our kilowatt hour consumption, this is how many kilowatt we need to put on the roof. Okay, and it's called regional factor, and there is a chart for it here, that chart, but you can do it per month or you can do it per year. Okay, so this chart, look at what the energy from PV system is kilowatt of PV, this is how much you have on the roof, multiply by the kilowatt hour over the kilowatt per year, or basically the number of hours per year. So that number here, so 75, that was per month. Regional factor can be 75 per month, hour per month, or it could be hour per years. What's the hour per years? How many total hour we have per year? 8,760 hours per year. Out of those 8,700 hours, in Tulsa, Oklahoma, we get 1,800 hours of one sun. So you put one sun for 1,800 hours in Tulsa, Oklahoma, and you will get the kilowatt hour from the kilowatt. So you're gonna put 40 kilowatt, 2 kilowatt, 1 kilowatt. You multiply by this number and you figure out how much kilowatt hour you're gonna get. Yes. Question?
It's off topic.
No, go ahead, ask.
Just it's not financially advantageous to do solar. Correct. I mean, like for your average consumer. Me as a homeowner, to put solar panels in my household would cost me $40,000 for my entire wattage income or total finance wise. If that makes sense. And then you only get a rebate of what, 30% Oklahoma? I mean, for other states, it makes a lot more sense to do solar panels than Oklahoma due to our sun positioning. Is that correct? And like Europe, you see a lot of solar panel fields.
So what's your name?
It's just
What's your name again?
Trevor.
Trevor is pointing to a very important thing, and that is the policy of the city or the state can really make things appealing or not appealing. So you will be surprised to know that the largest field of PV panels is in, I would think like Mexico or like someone hot, but no, it's in Ontario, Canada. And why is that? Like all the way up north, because it's the incentive of the government, basically. If the government give incentive, cancel taxes, or even subsidize the thingy because they are from the Green Party, elected by people who are like green fanatics or they really don't want any emission. There's other consideration that make people say we want solar power. So for in Germany, they basically panicked from nuclear energy after Fukushima, and they said no more nuclear. So what should we do? PV panels, because we don't have natural gas, we don't have oil, we don't have anything else in Germany. Let's just put PV panels. So the policy, whether it's fair or not fair, whether it's smart economically or not, can really tip the change, because we are at that border. I had one student before that used to work for a solar company that make the concentrator system, that heat, and he said our company is at the edge, like if that's just like the oil price go a little bit up, we make profit. If it go down, we get bankrupt. It's that sensitive basically, right? But as the technology get better, make no mistake that solar panel will dominate.
Is that technology on the panel or the battery?
Batteries is a key, right? Batteries is a key. Storage is really a key, because this number that I'm multiplying over here, you could have told me this number is for year long, but where is what I'm gonna get in the winter? When you told me you're gonna get 1800 hour in Tulsa, Oklahoma, and wow, so now if I get 1 kilowatt hour, I'm gonna get 1800 if I put 1 kilowatt in my roof, and a typical house require like 5 kilowatt, that would be plenty actually. So if I put 1 kilowatt, I'm gonna get 1800 kilowatt hour. Yes, year long, but chances are this will be mainly in the summer, and in the winter that system will not generate enough, and in the winter we will have to freeze to death because nothing will happen. So that monthly or like seasonal variation is a big deal, and unless the grid allow you to store in the summer and consume in the winter from it free of charge without penalty, those numbers need to be modified. Say that again.
So is that like a grid storage?
Right. So in some states they basically they are the what do you call it? The meter is a smart meter. So basically you generate energy and the meter go this way. You consume energy and the meter go that way. And the end of the month they basically figure, so what did you consume at the end, or did you get more than what you produce, or you produce more than what you consume, and they determine the price. But that's not really fair for the grid, because again, as we explained before, in order for the grid to be ready for you, that you will shut down your PV panel because it's cloudy, it's raining, it's whatever, and supply you, the grid need to have the capacity that supply your house at full rate without you running your system, and then that costs money. To have a power gas turbine sitting waiting for you to say, help me, I don't have sun. That gas turbine require money. And so that's why it's not really from the society point of view, it's not really fair to just be exactly the same price. No, you should lose money by storing in the grid, because the grid infrastructure require money to be waiting in standby mode waiting for you. Right? But let's leave this for someone in business school to find out what is the fair policy. But as us as engineers, what we need to know and be able to design is, if someone say, I have this load in my system, how many PV panels, what capacity do you recommend for me? We need to be able to do this calculation. And there is a big room for innovation and become famous and make money if you can figure out how you can store the energy. And the solution is not always just battery. Yes, let's let chemical engineering and electrical engineering worry about how we make batteries more and more efficient, but as mechanical engineer there is a lot of room for us to think about how we can make mechanical storage more efficiently. Okay, Tom, you had a question. That is an excellent point. So Tom is saying, especially for not North America, but like in Asia and Europe, because they are spread. If they are connected on a grid, then when someone have night, someone is, starting his morning, right? And so when they are in different time zone like this, it's super easy for them to shift the power consumption and production from one place to the other. Unlike in North America, where we are all basically on just like one time zone, kind of. If you are spread like this, that would be really, really nice. Yeah, that can change the heating load. Yeah, definitely. So, but that is an excellent point, and they already are connected in Europe. And I read somewhere, I don't remember where, that in the Second World War or the First, Germany and France, they were fighting with each other, but they didn't disconnect the grid. So I read that somewhere. We can Google that to see if it's true or not. So they were in war in each other, and they still were connected by the grid. Isn't that amazing if it's true? So there is benefit to basically connect over different time zone, and especially also there was this one project, I forgot how far they managed to go through, is that Europe basically one of the places where Europe can generate power is just across the Mediterranean in Africa, where they have huge sun, big desert, no rain whatsoever. You put your PV panel there and you get your one sun. Those number would be like Arizona or higher. You get the 2,000 or even more. So what is the maximum hour, by the way, we should expect? No, the hour per year. What is the maximum power we should expect? Like, what is our Carnot cycle equivalent of hours? No, we cannot get the 8,000 because there is night. I mean, we cannot ignore the fact there is night. But at least half the day, at least half the day, that's like the maximum ever you can imagine. So, I mean, so let's call it 4,000. So 4,000 is the maximum possible of one sun. And it's super hard because, I mean, part of the day the sun is really low. So you have to give the sun some time until it really hit up. Right?
That was one question. What causes the variation in the graph? Is it elevation or is it just...
So the question is, what caused the change in why those people in Arizona and New Mexico are so lucky compared to us? And we are at the same almost latitude. So I understand why Alaska is different from us, because they are higher, the sun comes with lower angle. Okay, I got that. But like, why in Tulsa, Oklahoma, we are not as good as New Mexico or Arizona? Cloud cover, rains, right? So the more the desert condition it is, the clearer the sky. So you can basically, that's why over here we have the largest solar thermal power plant in the whole world sitting over here. Alright? So back to Europe. So Europe was actually, they are planning to build the largest solar thermal power plant in Morocco, across from Spain, because you can cross just, a very tiny Mediterranean and you'll be in Europe. So you connect there and you get all the power downstairs. Right? And also, for example, Ethiopia right now is building the largest dam ever, 9 gigawatt of hydraulic power, and they don't consume 9 gigawatt. The whole country does not require 9 gigawatt. So from one dam they will get 9 gigawatt. So what are they going to do with it? Sell it, connect it to Egypt, then Jordan, then Israel, then all the way up to Turkey and Europe. So that idea of connecting different grids is basically a lot of Ethiopia. Ethiopia is like on the river Nile. Of course, it's to build that dam, you have to shut down the water, then the whole country will starve for like 4 years until you fill the dam. And that's why the US is trying to broker the deal between them. Otherwise, they will be a big deal. Okay, so what do we get from all this discussion? Seasonal variation, cloud cover, make different places respond differently to the PV panel sitting on top of the roof. The number that we want is from this chart. This is the regional factor, hour per year or hour per month. Okay, the unit will be kilowatt hour per kilowatt year or kilowatt hour per kilowatt months.
If you break this math out, it's really people per solar panel, you see a distinct variation as it comes from a Republican to a Democratic state.
This is beyond the content of this course. Let's leave this for someone in political science. All right. So this is the first way we will design our collectors. Okay, just using the regional factor. Okay, there is a little bit more sophisticated method, and we will talk about it after the break. So 15 minutes break.